Hi, I'm Mike White. I'll be presenting our work today on data-efficient modeling in task-oriented NLG. This work is also going to appear soon in the Coling industry track, so please see our paper for further details. I'm one of many Facebook authors of this work. In fact, going through everyone's contributions would probably take more time than we've been given. To this point, training high-quality neural NLG models has taken a lot of annotated training data, and that's a barrier to scaling up development across domains. Now, while pre-trained language models can help reduce data needs, they're too slow for a real-time dialogue system. So, as you can see from this input representation in the domain of conversational weather, our inputs are compositional tree-structured meaning representations, or MRs. Now, as you can also see in this target output text, the outputs are also tree-structured. Now, what this allows us to do is automatically check for correctness by making sure that these structural tokens in the output match those of the input. And indeed, we use this kind of check to define a metric we call tree accuracy. With bucketing, we just use one or a few data points per bucket. Our second strategy for data efficiency is to simply train jointly across similar domains. Our third strategy is to dynamically augment the data by plugging in new slot values for the values found in the existing annotated data. Finally, our last strategy takes advantage of the BART pre-trained language model. What we do is we run BART on unlabeled meaning representations to auto-annotate that data. That's similar to what happens in self-training. But going beyond self-training, we then distill BART's knowledge down into small, fast sequence-to-sequence models. In these results, we look at tree accuracy as a function of the data reduction rate, or the number of training samples. What we find is that across domains, the combination of all our methods works best. So for example, in Reminder, we find right here a very high tree accuracy with about a 90% data reduction. Meanwhile, in some simpler domains, we find that our simpler techniques also work well. So, given that the simpler methods sometimes work fine, we suggest matching the engineering complexity of the solution to the complexity of the domain. With this in mind, we conclude our poster as well as our paper with a runbook, which gives step-by-step instructions for how to apply the lessons we've learned in this work.